Welcome everybody to the module of Computer Security Basics number 2. We will be revising some of the computer security basics we need for understanding the issues of IoT and SCADA systems. The goals of this unit are to describe some of those tools we need for realizing cybersecurity protection goals, as they were introduced in the unit on Computer Security Basics number 1, which was presented to you by Simon Wiedemann. And we will be doing so in an abstract, conceptual level. And for algorithmic details, for implementations and more, I referred you to two places in the literature cited as 1 and 2, as implementations actually require much more time than we have for understanding. I would like to outline some special situations we have in IoT and SCADA systems, and I would like to lay a foundation for an interactive discussion we will have later during the summer school on the question, how do we connect these tools presented in my unit with the protection goals presented in the unit of Simeon. So let's have a look at the first part, which will be talking about basic tools we need in cryptography. The basic tools I would like to present today are one-way functions, their use in encryption and in signatures, hash functions, the issue of randomization, and questions of key management. So let's get started with one-way functions, what they are, how we can define them, and let's have a look at some small examples. The core idea of one-way functions is as follows. We have a computation, which is easy. The inverse of the computation is complicated, or, to put it more precisely, is typically complicated. So we have a function which is working on a set A of characters, of symbols. We have a look at a star, which is the set of words we construct over that alphabet. And one direction is easy to compute. The other direction, the inverse of that function, is typically hard. So, to have a short example here, we could think of a set of sets of 2 prime numbers. So that's like one domain in which we can look at the function of multiplication and multiplying 2 prime numbers together to the product of 2 prime numbers actually is pretty easy, whereas factorizing is typically hard. Let's have a look at an example. We start with 2 and 3, we calculate 6, that's a simple thing to do. Factorizing, it says, is typically hard. Now, we already understand there is an important detail in that notion of typicality. Not all instances of the problem have to be complicated. As in our example, factoring 6 into 2 times 3 is pretty much easy. It must be the typical instance, and expressing that notion of typicality might require a bit of a twist in formal definitions. So let's have a look into a more complicated scenario. Let's have a look at what is known in the literature as the RSA 785 challenge. We see 2 large numbers, multiplying them is easy. Factorizing actually is a very hard problem. Now, let's note a few details here. First, every factorizing problem which we first generated by multiplication is easy. RSA 785, if I start with these 2 prime numbers, results in a factorization problem, which is easy if I recall how I initially designed that factorization problem. Number 2, there are some factorizing instances which have particular easy properties. For example, let's think of 10 to the 300. Well, that's of course an instance which with a little bit of understanding of number theory is absolutely easy to factor. Hard is the typical rest. So after considering these nodes 1 and 2, the rest which remains is complicated. What does it mean, easy and hard? Well, often in cryptographic literature we find a recourse to NP-complete problems. And for some more details about NP-complete problems, have a look at literature 4, 5, and 6. There are many cryptographic mechanisms which use problems which are not completely known to be NP-complete. We just suppose they are NP-complete or they are complicated in some other form of notion. Also, we understand we might be using asymptotic complexity of the best known algorithms in literature to get a bit of a better understanding how to underpin easy and hard with some solid meaning. So, for example, if we assume that n is the number of binary digits in the input and assuming a particular computational model, computing the product is big O of n squared. That's pretty easy to calculate, but the inversion, the factorization of a product of two prime numbers, here the best known algorithm to date is big O of the exponential of n over a third times the logarithm of n over 2/3. So, and here we see there is an exponential inside of that big O, and that's actually something which makes it typically very complicated. We now could make a look at the formal definition of a one-way function. We will define a one-way function on strings of bits, so the words constructed over the symbols 0 and 1. And we have many of these different, in the essential GIST, equivalent definitions. We follow literature number 7, and we find there that we require two things. Number 1, it is easy to compute. This can be broken down into the existence of a deterministic polynomial time algorithm C, which on all inputs of x outputs f of x, and which is typically hard to invert. And now we see the twisted form of definition about typically being hard to invert. So there is for every probabilistic polynomial time algorithm A, and every positive valued polynomial p, and for sufficiently large n, the probability that f essentially correctly is doing the inversion here is smaller than 1 over p of n, where we have to look at the probability. un is uniformly distributed over the words of length n over 0 and 1. And the probability is taken over all possible values of un and all possible random inputs for that probabilistic algorithm A. So we understand that's already kind of quite an involved way of expressing that a particular algorithm is difficult to invert. So what does this mean? A probabilistic, we might read that as powerful because it has access to random oracles. A probabilistic polynomial time algorithm which is attempting to invert f, and inverting f is what we express by that nice formula of f of a of f of un and 1 to the n equals f to un, fails to do so. The probability, and using the probability in this definition, gives a notion to our concept of typical. The probability of success is smaller than 1 over p of n for arbitrary p and large n. Hence, the probability is really, really small. And that we have the input of n copies of 1 in the algorithm A that is here for some technical reasons only, in which details we will not involve ourselves at this unit. Now we see, as a side note, rigid studies of mathematical cryptography needs loads of hard complexity theory. And actually, it is not even known whether one-way functions in this strict sense we right now defined really exist. We will not pursue the rigid path. Often, this rigid path buys us no hard results, leads into more mathematical details, and sometimes is even obscuring our understanding what is going on. But we keep in the back of our minds that it's possible to lay a solid foundation about these details when we are talking about typically difficult to invert. There are also one-way trapdoor functions, and the core idea of one-way trapdoor functions is that a computation is easy, that the inversion of the computation is complicated, as we just discussed it, but that the additional knowledge of a trapdoor makes the computation, the inversion, easy again. So let's have a look at the next slide. We again have one direction which is easy to compute. The inversion is hard to do, but given the trapdoor, it is easy to invert that computation. Now let's ask ourselves, how could we make some nice use of this interesting concept? Could we leverage this core idea into something? And when we think back of what we know from encryption, from authentication, from signature, we get an understanding that there might be some interesting connection. Encryption means only when I know a particular secret, such as a key, I can read and understand something. Authentication means that the ability to do something extremely complicated proves my identity because I'm the only person knowing that particular trapdoor which makes this computation easy. And if I attach this complicated thing somehow to a document, this might demonstrate my approval, and it's only my approval because only I have access to that particular trapdoor. Of course, implicit behind these concepts, there is a socio-technological rule which is very important. The rule is as follows: you shall not share your secrets with others. That rule is a socio-technological rule because, as we will see in the next slide, technology cannot enforce it, but the user with access to these secrets must act upon this. The rule is implicit because it's rarely spelled out clearly enough in the cryptographic literature, but we have to be careful as well a little bit because, well, normal users adhere to this rule, but attackers might freely share secrets with others, and we will see that for particularly the case of symmetric encryption, this is an important thing because here every key holder must trust every other key holder, and this socio-technological rule is a very important part of the game. So let's have a look at a nice caricature by XKCD, which shows us the importance of this socio-technological rule. So in the imagination of the crypto nerd, two bad guys find a laptop and they are completely frustrated because they realize the laptop is encrypted. They are speculating about building $1 million computing cluster to crack the code, and then they understand, oh my god, that's not going to work out because it's a very long key length RSA algorithm, and damned, the evil plan is not going to work out. So that's what a crypto nerd believes. But what actually could be happening, that the two bad guys find out the laptop is encrypted, but probably the owner of the laptop has access to the key. So they go to a construction shop, they buy a $5 worth wrench, and they will hit that poor guy with the wrench and threaten him until finally that person devours the password. That's the importance of the socio-technological rule. Let's move on to the next section about encryption. And for the beginning, let's talk about a number of basic notions we need here. Plain text is what everybody can read. Encryption is the process of transforming the plain text into ciphertext. Nobody can understand or read the ciphertext except those who have access to a secret and allow us to invert that function. So we also understand the processes of encryption and decryption now, and we would like to have a little bit more formal look on the first process on encryption. So let's say M is a set representing messages, and usually we take A as a finite set. We call it an alphabet. That could be, well, in computer science, it's most of the time it's bits. It could be like the letters A to Z or the characters of 7 or 8-bit ASCII or what you want. And we look at M, the messages being either fixed lengths or variable lengths words taken over A. Depending on the length, we are talking about block ciphers or about stream ciphers. And we will currently not look into different sets for plain text and ciphertext messages, so M is the set of messages we can write. Let's say K is a set representing our keys, and R shall be a set representing random numbers. Now let's have a look at encryption. Encryption is a process which takes a key and a message and produces the ciphertext corresponding to the plain text of M. Decryption is a process which we hope will invert this thing, and we need a third thing for a formal understanding, which is key generation. And in key generation, we get a process which constructs for our use two matching keys. So we start with a random number. We use this random number in the key generation process, and as a result, we get a decryption key and an encryption key. And if we look at a decryption key and an encryption key produced by the same random value, we say that these keys are matching to each other. They are generated from the same randomness, and the decryption key hopefully decrypts what we have encrypted with the encryption key. In order for these things to work out properly, we need two important core properties. Number one is pretty obvious. Decrypting with a matching decryption key undoes the encryption with the encryption key. So that's what we see here. If I take a message M, I have matching keys with the same random value. Encrypting then decrypting leads to my message. And the second core property is, well, okay, here we have it again. It is very difficult. And I hope you believe that this phrase, it is very difficult that this somehow can be properly formalized. Actually, this is done in the cryptographic literature. So it is very difficult to obtain the plain text from the ciphertext without knowing a decryption key which is matching the encryption key. And We believe, we had a look at that already in the trapdoor function, we believe that there is a possibility to find a reasonably nice mathematical description for what this "it is very difficult" means. It is our basic understanding as users of cryptography that these things are going to work out mathematically nicely in the typical case. Now, for encryption, we should look at 3 different forms of algorithms. In the symmetric encryption case, we have one key. So the decryption key is identical to the encryption key. There is only one secret key. The use of the keys, well, we understand decryption and encryption are using the same key, and who knows the key can encrypt and decrypt. The access to the messages, again, obvious. Sender and receiver are using the same key. Of course, we understand there is that requirement of secrecy. It corresponds to that implicit socio-technological rule. The key must be kept secret by all parties. That's the important thing here. Sender and receiver, so obviously there will be more than one person knowing about that key, and these people have to trust each other. So we already understand there might be some interesting problems connected with symmetric encryption. Let's have a look at those. Problem number 1 is, how would we distribute the secret key? Key distribution needs protection. There could be an attacker listening into the key distribution process, so we need encryption, which needs a key, which needs key distribution. So we understand we actually do have a bootstrapping problem here for distributing the secret key, and we will be talking about that a little bit later because that's a separate subsection of our unit. It's hybrid encryption. And there is a second important problem, the loss of keys by others. Well, of course, I personally will always try to guard my key, but we could have the following situation. Alice, Bob, and Carol agreed to use symmetric encryption. All of them have access to that one secret key. Now let's assume Alice loses the key, and the attacker now can read ciphertext, which Bob was writing to Carol. So a failure of Alice affects the communication between Bob and Carol. And that's actually a trust situation. We don't really feel so happy with it. And the solution for this is asymmetric encryption. But for all the other scenarios where we are not bothered about problem number 1 and about problem number 2, we have, with symmetric encryption, a very nice tool for helping us. And that tool actually is used in all the applications of hybrid encryption, which we will be learning about in a moment, which you will be using whenever you're ordering in a classical internet commercial website. Let's have a look at asymmetric encryption. In asymmetric encryption, we have 2 different but matching keys. The use of the keys now is different. Encryption uses the encryption or public key. Decryption uses the matching decryption or private key. So let's have a look at the capabilities. Those who know the encryption key can encrypt for a person, and only that person knowing the matching decryption key can decrypt. And actually, only one person, the proper recipient of the message, should know that decryption key, which therefore also is called private key, because that person will keep that key private. Whereas everybody should be able to encrypt for that particular person, So the encryption key also is made as widely known as possible. It is therefore also called the public key. So the sender uses the public key, the receiver uses the private key, and we understand again the rule about secrecy here. The private key must be kept secret by the one and only owner, and the public key must be publicly available and of course associated with the correct one and only owner. And that "and" actually is written bold-faced because there is again one interesting problem hidden behind, which we will be talking about in the section on key management. So we understand that in the asymmetric encryption scenarios we have the question how to distribute the public key, and actually it's a non-problem. The encryption key is public anyhow, and the decryption key is supposed to be secret. So we actually get two resulting problems from that observation. Number one, how would we ensure the distribution of the correct public key? It's actually that problem we will be looking at in the section on key management. And how would I keep the private key secret? And again, we will debate this a little bit when we think about key management in general. Let's have a look at some of the encryption algorithms, some examples. So we have a wide range of asymmetric methods and of symmetric methods, and I'm giving you RSA and ECC as the most important asymmetric methods and AES as the most important symmetric method. As you see on these slides, there are quite a number of more algorithms, some of them being broken. They either have too short keys as the data encryption standard, or they have longer keys but fail to do so in a proper way as the DDS algorithm, for example, or they are using a mathematical problem in a, well, as one discovered later, wrong way, which is the case for the Merkle-Hellman-Knapsack problem. And there is a wide range of more algorithms, and I am giving you two links for clicking. Look at the table in Wikipedia here, and you'll find a long list of more algorithms if you desire to know more details here. There is one category which we still have to talk about: hybrid encryption. Let us first review what we learned about symmetric and asymmetric algorithms. If we look at the implementations, we see these symmetric algorithms usually are quite fast, whereas the asymmetric are typically slow. And we also see an aspect with regard to the trust situation. In the symmetric algorithm scenario, we have to trust everybody who knows about that key. Every key owner has to be trusted. Whereas in the asymmetric case, I only have one private key owner, so I only have to trust myself, actually. I have to trust that I take proper care of my private key, and then everything is fine. So in the symmetric case, the problem is the key distribution, whereas in the asymmetric scenario, the problem, we will be talking about that shortly, is the key authenticity. Do I have the right public key for the right person? And now, of course, if you have such a table of comparing advantages and disadvantages, well, we always want the advantages of both cases. So, we are using asymmetric encryption for distributing the secret keys of symmetric encryption. With asymmetric encryption, that is a nice thing to do. There is no problem for bootstrapping. Well, we have one problem with key management, but we are going to talk about that. And there is symmetric encryption, and as soon as we have distributed the secret key for symmetric encryption, we now can use the fast speed symmetric implementations for payload encryption. But of course, we understand this means that the involved parties, be it persons or be it programs, should keep the key secret. Are they actually doing that? Well, we trust that the key will stay secret for some time, but we actually cannot guarantee that for a longer period of time. So after some time, we will expire the symmetric key. We will have recourse to our asymmetric algorithm again for redistributing a fresh secret, a fresh symmetric key. Let's have a look at the next section where we are discussing signatures as one of our tool sets in basic cryptography. Now in the signature scenario, we have M being a set representing messages. As usual, we also will not use different sets for messages or for signatures, for signed messages. We have again the set K for representing keys, and we have a set R for representing random numbers. And again, from a more systematic approach, we have three functions: signature, verification, and you might have guessed it, key generation as the last one. Signature is a process which takes a key and applies the key on the message to provide a particularly new document, the signature. And verification now takes a supposed signature, S, a message M, and a verification key E, and now checks: is the signature S a proper signature which verifies under this particular key E, and as a result we get true or false. So a Boolean value which indicates the validity status of the signature. And it's important to see that the validity status depends on the signature and on the message, on these two parts. Well, of course, we are using keys again, and the key generation again is a process which starts with a random value and produces a signing key and a verification key. And it's just the same game as we had it with encryption and decryption. Signing and verification key, if they are produced from the same random value, are said to match each other. Again, we would like to look at two core properties in order to get an understanding when these syntactical scenarios, these three functions, are working together in a proper way, really producing correct signatures. And of course, again, the first property is pretty much obvious. It's verification. If I do a verification using a verification key, which is matching the signing key, in that case, the verification says, yes, everything is fine. Now, what about the other side? Well, there is a particular property I get by knowing the matching keys. And of course, we will again have something similarly as we observed it in the encryption case, that it is very difficult to produce a signature for a message which verifies for a verification key without knowing the signing key. So, not knowing the signing key, it's problematic to get a valid signature. And again, we trust that this "it is very difficult" can properly be formalized in some mathematical way. Now let's have a look at the signatures and the asymmetric algorithms, because actually the setup of the signatures and of encryption looked very, very similar. So actually maybe there is some very close connection between encryption and between signing, and we are going to try to find out about that, having a look at asymmetric and symmetric scenarios. we will make the following observation. Only the holder of a decryption key can decrypt. Only the holder of a signing key can produce valid signatures. Every holder of an encryption key can encrypt, and every holder of a verification key can verify. So actually it really looks like decryption and signing and encryption and verification are similar, and if we have a closer study of the definitions and of the core properties, we can conclude. We can use asymmetric encryption algorithms for signing, where encryption corresponds to verification and uses the public key, and decryption corresponds to signing and uses the private key. Now we are curious, can we also use symmetric algorithms for signing? Well, that's an interesting question, and it depends a bit on the power of proof we want and on the application of the particular scenario. Let's think of symmetric methods. Every owner of the private or public? Well, in symmetric algorithms, we only have that one secret key. Every owner of that one secret key can sign and verify. So let's assume Alice, Bob, and Carol share one secret symmetric key. And let's assume Alice knows that Bob or Carol has signed and not Mallory. But has Bob signed the message? Or has Carol signed the message? Alice can't distinguish these two situations, because both Bob and Carol have that secret key. Mallory, the bad person, does not have access to the key, so I as Alice know that Bob or Carol have signed. So we understand a symmetric signature has a power of proof on cooperating, trustworthy parties. It means that Alice knows there will not be a conflict between Bob and Carol, whether Bob or Carol has signed. We will not have to prove in court it was Bob who signed and not Carol. And we trust that nobody hands out that secret key. So we understand symmetric signatures have no power of proof towards third parties, such as courts, a judge in the court room presiding over a quarrel, and therefore they are actually not really used. There are some small exceptions with off-the-record cryptography where we might see things which might remind us of symmetric signatures, but we will not go into details in this course about that. In the situation of asymmetric methods, we understand only the owner of the private key can sign, and we have that assumption that the user keeps the private key private. It's that socio-technological rule. The signer only has to trust herself, and therefore the key will remain private. Under that assumption, every third party can verify the signature, and asymmetric signatures have power of proof towards third parties. In court, it can be proved that a certain document had been signed, therefore it's the method of choice. Let's have a look at the next element of our toolkit, which are hash functions. Why do we need hash functions? What are hash functions? We can take as informal definition a hash function as a function mapping an arbitrary document, a long document, several thousand, 10,000, maybe even millions of characters, to a very short hash value h of d. Often k is 0, 1 to the nth, with n relatively small. Sometimes it's taken to be like 30 for the case of the generic hash function. It will be different in cryptographic hash functions, which we'll be discussing on the next slide. So as an example, we could say, well, if we take like a document consisting of letters alpha, 0, 1, 2, and so on, we could add these characters. Characters actually might be part of a ASCII 7-bit, 8-bit ASCII, so we can consider them as numbers. We can add them up. We can calculate the sum. We can calculate the modulus by division by, say, 1024. And we could have the situation that the Bible, for example, has a hash value of 271, and maybe the US Constitution of 314. Hash functions, in a certain way, correspond to a kind of numbering of documents. And we could think of the situation where we have maybe 2 to the 10 equal 1024 storage locations. Given a document with 7-bit ASCII code, we can calculate the hash value and we could store the document in location number H of D. So it's really like calculating the location where that document is saved on hard disk. Now, we understand that actually works for a small number of documents, only, let's say, 20, 30 documents, it probably works out. But as soon as we are looking into a really large number of documents, we risk having hash collisions. So actually 2 documents could have the same hash value. For storing, that's an interesting situation. What can we do? We can store different documents on the same storage place. So we have kind of like to split that one storage place if there is such a hash collision. And if you look into what the database guys are doing, it's actually thinking about how can we split up hash value stored documents in a database. Of course, that observation prompts the idea that we could make the length of hash values a bit larger. Let's try it out. Let's go beyond n equal 20, n equal 30. Let's try a little bit larger and like 256. Doesn't sound very large actually, 256. But we should keep in mind that we have 2 to the 256 possible hash values. And 2 to the 256, actually that's 10 to the 77. Oh my god, that's really a large number. And should, for some reason you don't believe that that number is large, calculate 2 to the 256 in the full precision. You will see that really becomes a big number. We will never ever on that planet have that many documents. So the risk of hash collisions is virtually zero, at least if we restrict application of our hash functions only onto documents we eventually will see on our planet. Okay. We will never have that many storage cells either, so we shouldn't be worried about that too much. But, well, collisions as such still might be easy to find. Let's observe the following thing. Job set, let's say job set and Bob set are the prefixes of 2 documents, and then there follows after this short prefix there follows a very long rest document. And we understand that job set and Bob set, if we look at the positions of the letters B and J in 7-bit ASCII, we understand that's kind of like that change just means adding +8 to the hash value. So we see it's actually easy to construct collisions, even with meaningful documents. So, that looks like a little bit of a contradiction to what we looked at first. And actually, it is easy to translate here changes in the hash back to changes in the document. And now we became curious. It looks like there is a small deficiency in this concept of hash functions, and our question is, we became curious, our question is, can we actually fix that? And if you're able to fix that, can we use that for something meaningful? So could we have something like a function from documents to hash values? And what about the inversion of that function? So from meaningful documents to hash values, it's easy to compute, but maybe the function is hard to invert. We actually had that early in our unit, so there might be something interesting to that, and we will look into these types of things. So we nevertheless might have collisions as such, because there are so many more documents than meaningful documents than possible hash values. So we will have collisions. So maybe the Bible has the same hash value as this completely rubbish document as SJF, 7Z, and so on. You see it on the slides. But wait. There will be much less meaningful documents than hash values. So if we restrict ourselves on meaningful documents only, that actually still could be working out. Okay, I think we got a little bit of a motivation. We understand where we are heading to with hash functions. Now let's have a look at some of the cryptographic core properties of cryptographic hash functions. There are many others that I'm presenting today, but let's have a look at those three properties usually connected with the notion of a cryptographic hash function. Again, we understand that we will be using the words it is difficult and it is easy, and we have that understanding that it means something which can be broken down into probabilistic algorithms, into probabilities, and so on. We will not be doing this in our unit, but you will find in the literature references places where this is done to a very high degree of precision. Number one, collision resistance. It is difficult to find any two documents, D1, D2, with the same hash value. H of D1 equals H of D2. It is difficult to find a collision, so the hash function is called collision resistant. The second property is pre-image resistance. Given a value V, it is difficult to find any document hashing to that value. It is resistant for forming pre-images given a value. And there is a slight variant of that property, which is called second pre-image resistance, which means if we have given a document D1, it is difficult to find a second document, a second pre-image of that value of H of D1. And we understand these three properties are somehow a little bit interlinked with each other, and we can study them closely. Most often, for designing a cryptographic hash function, one tries to use the construction principle, which is known as avalanche construction principle. Let's assume we have an input to a hash function. We flip one bit of the input, and typically half of the output bits are flipped. But half are flipped, and we actually shouldn't be able to predict easily which ones are flipped. That's the way how usually hash functions are constructed, which then in practice show these three properties. And as I mentioned, there are other interesting properties of hash functions which we can be studying as well. Let's have a look at the particular use of hash functions for message authentication. The task is a MAC, a message authentication code. Alice sends a message to Bob, and Eve may listen in. This is fine, an eavesdropper is permitted in that application. But the bad guy, Mallory, the bad person, should not be able to modify the message without Bob being able to detect that modification. So the solution might be that Alice and Bob agree on a secret pre-image resistant hash function H. Alice sends the document D and sends the MAC value we get by applying that secret hash function onto the document. Bob receives a document, let's call it D prime because we don't know whether it's the same as D. Bob receives the document D prime and receives a MAC value M prime, and Bob now checks if H of D prime equals M prime. Let's study some of the possible attacks. Let's assume Mallory modified the document D to some document D tilde. How should she now modify M? She actually cannot calculate the hash function because she doesn't know the hash function. And even then she cannot go backwards from M since the hash function is pre-image resistant. So in practice, Alice and Bob will be using an established cryptographic hash function, let's say the SHA-3, and to get their own secret hash function, they derive a particular hash function from that by prepending a shared secret kappa in that case, and use the hash function in a way that it's prepended, kappa is prepended before the document, and then the established SHA-3 hash function is applied. Let me just point out one particular weakness if we are using this approach, which is the length extension attack. There are many established hash functions, think SHA-1, SHA-2 or MD5, which are using a construction which is known as the Merkle-Damgard construction, and I give you some details if you would like to find out a bit more about that construction. This particular construction would allow it for an attacker, for Mallory, to make the document longer by adding a suffix to the document and calculating the hash of the longer document from the added suffix and the hash value of the shorter document, which is available for the attacker by eavesdropping. So the solution here, of course, is to use a smart multiple hashing, such as is known as HMAC, or to really use a good hash function as SHA-3, for example. One of the reasons why one discarded SHA-1 and also SHA-2 and invented another hash function SHA-3. For the power of proof, we here observe that Alice and Bob and Carol are sharing a secret hash function H. Alice sends the document and the hash function D to Bob. Bob now can check if D has been tampered with. But Bob now cannot know if Alice or Carol have calculated H of D. So we again see, for protecting the document, this is nice, but for Bob to know whether Alice or Carol has sent it, we again need some additional information, some additional trust assumption, and we again see there is a similar lack of proving power as we discussed it when we tried to apply symmetric methods for signing, which is just similar here because we only had one symmetric, one shared secret key as in the case of the symmetric algorithms. Now let's have a look at the use of hash functions for signing in yet another scenario. Let's say H is a cryptographic hash function. For the proving power, we could say that signing, and here I mean signing in that proper asymmetric way as we learned about it, signing the cryptographic hash of the document D is equivalent as signing the document D itself. So we have to think that through a little bit with the properties of a cryptographic hash function, and then we see it amounts to the same result. But we have to be careful a little bit here. First, we will never sign a hash value v unless we have checked ourselves that the document we want to sign really hashes to that particular value. We might end up signing a completely different document unless we ourselves have checked that property. And a second aspect. For signing and for encrypting, we actually should be using separate key pairs. It's essentially the same algorithm, the same method, so we might come up with the idea for using our signing keys for encryption and vice versa, but we might end up sending out confidential information in that case. And let's have a look at one interesting story here to see the connections. Alice encrypts a PIN code and sends that PIN code to Bob. Mallory intercepts that message M and asks Bob to sign that message M, and Bob, naively ignoring our caveats, signs the message and sends the result, the PIN code, to Mallory. So in effect, Bob has encrypted a message, whereas he believed he was signing a message and sending the obscure result to Mallory. So to distinguish these roles clearly, it is necessary to take care at these two caveats we just had a look at. Now let me give you some additional sources about cryptographic hash functions. There are some sources about non-cryptographic use of hash functions. There's a link to cryptographic hash functions and a link as well as literature reference to cryptographic hash functions with some additional explanations, and as well there are lists of cryptographic hash functions which you can use as links in the document. There is another element we have to look at, which is randomization. Why would we need randomization? Let's have a look at the following dialogue. Alice is sending something to Bob. Obviously, it's somehow, encrypted. Bob answers to Alice with 444477771214. Alice sends another message. Bob gives, we already know that answer. Alice sends another message to Bob and, we recognize this ciphertext 444477771214 again. So as a curious eavesdropper, we are starting to pose some naive questions to which plaintext we want to know. Does 444477771214 correspond? What if it corresponds always to the same plaintext? What could this plaintext be? So, shall we have a break in our presentation now? And the answer is 444477771214. Maybe it makes sense, maybe it says yes or no. Could be the case that it always means yes. So we understand there are a number of attacks which might be possible if we have no randomization. Deterministic encryption means a plaintext P always encrypts to the same ciphertext C. And that's what we have studied thus far. Our encryption process did not contain randomization. We only had randomization in the key generation, if you recall. So, deterministic encryption allows at least the following attacks. Number one, a dictionary attack. I can build a dictionary of ciphertext plaintext blocks when for some reason the plaintext is leaked. I somehow learn about the question, is there good weather today? And the answer is 444477771214. I look outside of my window, I see a thunderstorm is going on, and I understand 444477771214 probably means no. My dictionary starts building up. Number two, a replay attack. Obviously, the ciphertext, that one particular block of ciphertext, somehow might make sense to the recipient. I don't know what it means. I have no dictionary-based translation, but I simply send it again, and I might produce confusion on the other side. And a third attack, which we could call a correlation attack on context and communication. We observe for that purpose and abuse correlations between ciphertext and real-life contexts. Let's say, after Alice sends a particular message, always an armored car arrives at the bank, and we observe that. And now we want to rob that armored car, so we send that particular message as an attacker, and we know there will be an armored car arriving at the bank, which we can attack. Or, when Alice receives a particular message from Bob, she provides a particular answer, let's say 1315 to Carol. So let's send 1315 to Carol as a fake message, and let's confuse these guys with their communication. And finally, there could be a key guessing attack. The key guessing attack now is an attack which works in particular for a asymmetric algorithm called the RSA, the famous RSA algorithm. I will not be going into the details of the inner workings of the RSA algorithm, so you might want to have a look into the implementations to understand that part in a little bit more depth, but all these implementations need a bit more time than we have in this introductory module in our summer school. So, in RSA, the public key contains a product of two large primes, namely P and Q, and the N is part of the public key. Factoring, knowing the factoring of N, allows the construction of the private key from the rest of the public key. Factoring is difficult. So, we have a problem here. Now, let's obtain two public key N values. And let's hope that due to some bad form of randomization, they are sharing one prime factor. Let's say N1 is equal to P times Q1 and N2 is equal to P times Q2. That actually shouldn't be the case, because these P and Q, when you're calculating, when you're determining as user of RSA your public key, you kind of like produce two random large prime numbers, and it shouldn't be the case that you have the same prime number, but due to some lack or some bad randomization, it could be the case that my N1 and that Bob's N2 share that P. And now, calculating the greatest common divisor, the GCD, is actually a very fast process. And so we could calculate the GCD of N1 and N2, which actually should be 1 normally in the generic case, but in our particular case, of course, it is P. So I know the P, and knowing the N1 and the P, I can calculate the Q1, and the same with Q2, so I have factored both N1 and N2, and I can use that to derive the private key of the two victims here. And actually there's a very nice publication here which shows that there is a significant number of cases where that actually really occurs in network devices. We will be coming back to that a little bit later. So randomization is a very important thing. We need it for probabilistic encryption and random padding. The solution of our problem is probabilistic encryption. And there are actually a wide range of probabilistic encryption methods. The most simplest being we pick a random number and we prepend or append or somehow smartly interleave the plain text with the random value before we do the encryption. As a result, we get a different ciphertext at every encryption. Well, almost. Maybe not at every encryption, but a high chance for making these things difficult for the typical case is the sufficient thing. Probabilistic encryption almost always encrypts to a different ciphertext C, and that's what we want to have here. Encryption, of course, no longer is a function of a key and a message, but a function of a random value of a key and a message, and it yields a ciphertext, and it includes that random value. There are a number of other places where we also might need randomization. Random padding as a measure of dictionary replay and correlation attack prevention, generating fresh keys for asymmetric keys. When you start to encrypt, we have that, signing, and we need some form of randomization here. That's rather seldom. You usually use your asymmetric keys for a number of months or even years. Generating fresh symmetric keys is a different scenario. You might recycle in hybrid encryption. You might recycle your symmetric key every other minute or so. And there are things like challenge response protocols where you want to generate fresh challenges, and many scenarios in cryptography where we might use randomization. So the question, of course, comes up: how should we actually randomize? There are two excellent methods: quantum mechanical processes and thermodynamical processes. The best actually is the quantum mechanical process, because according to the contemporary understanding we have in physics of quantum theory, there are quantum mechanical processes which are believed to be truly random. For example, the time between two radioactive decay processes. So I have like uranium atoms which I observe, and from the first, they decay once in a while, from the first decay event to the second decay event, the time I observe has a particular randomness. For computer science purposes, it's better not to require uranium, but to look at the Zener diode and to look at the voltage across the Zener diode and the connected quantum tunneling effect to get random quantum mechanical processes accessible to a chip. In the thermodynamical scenario, we believe that the processes are random due to the incredible complexity of the system. So we might look at the thermal noise of an amplifier, we might look at a lava lamp, the behavior of the liquid in a lava lamp, which, if we wait long enough, also shows randomness. There are other forms of randomness we could look at, for example, system randomness. We look at events in an extremely complex system. Let's say we look at arrival times of Ethernet packets at a large server. We understand that's not really truly random. So we understand there might be particular interdependencies between packets. If there is like a ping packet sent to a server, most likely very soon the server will answer with a reply to that ping packet, and it's actually not really random, the packet arrival and departure times in a server. Similarly, the number of files in a file system has a random aspect, but it is somehow weaker than in the quantum mechanical case. It needs some post-processing. And the same situation we find with user randomness. For example, we look at the time between two keystrokes, or we ask the user to press some random keys, and most users are pressing keys which are located in the center of the keyboard and not to the boundary of the keyboard. And there is pseudo-randomness. Algorithms which produce sequences of numbers which are not random at all. They follow a strict order determined by the algorithm, but not knowing the details of the algorithm, it's hard to predict them. So they look like pseudo-random numbers. Again, they need some post-processing. Let's have a look at our final section, which is key management. We had a look at 3 types of keys. So there are actually private keys of asymmetric algorithms, and the goal is they must be kept private, secret by the owner. How would you want to store them securely? There are the public keys of asymmetric algorithms, and the goal is they must be publicly connected with the correct owner, and the problem is how not to confuse the owners. And there are secret keys of symmetric algorithms. They must be kept secret by all using parties, and the question here is, how would I distribute them confidentially to all involved parties? Let's have a look at the problem of private keys. How can I store a private key securely? Well, there are all kinds of interesting attacks which might take place. They could be stolen by a keylogger. They could be found by an administrator in an unencrypted backup. They could be sent to a file server in a local network which is not using encryption. There could be a curious student using a packet sniffer at a computer science lab looking at these traffic. It could be an overly curious program which sends the private key to the manufacturer, and it could be under the collection or control of a virus. So there are all kinds of different attacks we might see. So we really must think about that problem. And I want to offer a number of solutions here. Actually, you could learn the key by heart, which is probably a bit difficult here. You could have the key file encrypted with an additional, maybe shorter key, which shifts the issue only to that storage of the additional, probably weaker key. A key could be stored on a hardware device. Now, what about the attacker extracting the key from the device, or the owner losing the device? So we again have to come up with some fantasy to counteract these attacks. And we could generate the key on a cryptographic device, never allowing the key to leave that device. It's protected by hardware, and actually that's a very nice approach, but it looks convenient, but it still has quite a number of issues to take care of. And as we see, we can find solutions, and what we always have in cryptography, when we find solutions, we yet again open up with these solutions quite a number of other attack vectors, which in consequence to inventing that solution we have to take care of. Let's have a look at the problems with the cryptographic device. The crypto operations now must take place on the device. And now the question is, how would I know that that device is signing the correct document? Maybe this device was built for the sole purpose of me having signed a particular fake document. That's the only reason why I got sent that document from the manufacturer. So I would like to have a possibility that I can display that document, which means the device has to be larger. Or I use a small device. There are a number of USB technology-based devices, but in that case, this device has to trust the computer to send the correct document for signing. There could be incorrect randomization, which might allow prediction of certain keys. Keys might be leaked from that hardware. Loss of that device might mean loss of the key. It's no longer accessible to me. So there are numerous problems which might be connected with that. Let's now have a look at a second key management problem connected with public keys, which is the man-in-the-middle attack. In this scenario, Alice sends to Bob without any encryption. So Alice sends to her iPhone, hello, the iPhone sends hello over the network. Hello arrives at the Mac of Bob, and the Mac of Bob displays that hello to Bob. Now let's make that a little bit more secure. Alice sends to Bob with encryption. We see the message from Alice to her iPhone. Her iPhone sends hexadecimal 1347 and a bit more in order to send that encrypted message. That message arrives at the Mac of Bob, which correctly decrypts it into hello. And one day, the following happens. Alice sends hello to her iPhone. Her iPhone sends some different encrypted message, but it looks encrypted, 8899, it's not plain text. And at the Mac of Bob, yet another different message arrives. So Alice isn't worried because the output of her device clearly seems to be encrypted and she cannot check that encryption by heart. She needs her iPhone cryptography for that, and Bob sees the input to his device seems to be encrypted, everything is fine. But neither Alice nor Bob, from their own local perspective, can understand that the ciphertext which had been sent is not the ciphertext received. We see it. 8899 is sent and 3437 is received, so we are very much alarmed. What happens at that wiggly line in between? And well, the messages are not so much different here, but, well, hello or hi. So let's have a look at our next slide where we see an explanation of what is going on here as a man-in-the-middle attack. Because what we here see as weird thing going on finds its explanation by Mallory sitting in between, Mallory encrypting information, receiving the information from Alice, sending something out again towards Bob, and in some way manipulating, changing what is going on. It could be in that naive way that Mallory is just reading, as we see it on this slide, but it could be even much worse. Mallory could change the message, manipulate it, read it, do whatever she wants with that message. And actually, the problem here is that this man-in-the-middle attack amounts to a sender encrypting to a different person, to a man in the middle, instead of the correct recipient. The man in the middle decrypts, reads, maybe modifies the message, and then re-encrypts for the original target. The reason we understand from our global perspective is a confusion of public keys. Instead of the public key of the recipient or signer, the public key of the middleman is used. In our example, we saw a use of that attack on encryption, and of course it is also possible for signatures. So we understand we have to really find solutions for our public key scenarios, and this solution is a certificate. A certificate being a statement which connects the identity of a person, however we want to define that identity, with a public key which really belongs to that person, and the certificate now is signed or otherwise confirmed or trusted by an entity which vouches for the correctness of this connection. And there actually are three possibilities how we can organize that trust in that vouching entity. One possibility is centralized. There is like what we call a public key or certificate infrastructure. The second possibility is that we use it in a distributed scenario in the so-called web of trust. And the third possibility is to use a separate verification, a second channel, by which we find out that this really is the correct public key. The essence of the concept of the problem here is we must make sure, do I really have the public key of George if I want to encrypt for George? Otherwise, I could be ending up encrypting for a man-in-the-middle attacker.
So, for establishing this identity, we could think of making use of trend. Trend is a trusted entity by definition. We say he is trusted. We don't further question that. And trend operates as a certificate authority, a CA. So Bob meets Trent and presents his passport. And then Trent produces a document of the following form. The public key of Bob, and he now knows how to identify Bob. He is born on the
2nd February 2022 in Berlin. He has this and that passport number, he has this and that email address, and so on. And the public key of Bob is the following value, which we here have encoded in hexadecimal values. Then Trent signs this document with his private key. And now let's see how we can use this identity. Alice wants to communicate with Bob. Therefore, she needs the public key of Bob, and her understanding of Bob is exactly that information, that Bob is identified by birth date, by social security number, by email address most likely in her case. And she needs the public key of Bob. So she asks Bob to send her the certificate. Alice finds the public key of Bob in the certificate. She sees the signature of Trent, she checks the signature of Trent, and she trusts Trent by definition. Now, she knows if the certificate was authentic, she therefore knows the correct public key of Bob. Now, of course, we see there is a small bootstrap problem. How would Alice get the public key of Trent? There are a number of approaches here. It could be like a public registry where we say, well, we assume that Alice trusts this public registry. There could be a key store. The key could be encoded by the manufacturer into the operating system. There could be key pinning, like the manufacturer encodes the public key into the software, into the firmware. Well, and there could be a recursive solution by yet another certificate. And of course we understand a recursive solution might eventually will have to terminate in one of the three scenarios like registry, key store, or key pinning. And the other two approaches we talked about are working essentially similarly in constructing a way of establishing trust into the public key. Now, we have collected quite a number of cryptographic instruments, but we would like to understand what are their particular challenges for IoT and for SCADA cryptography. We understand there are particular issues where these things might go wrong, might pose big problems, and they are behind numerous of the attacks we see against IoT, against SCADA systems. So in the second part of the presentation, which will be considerably shorter than the first part, we will have a look into some of the following issues. We will be talking about updates, about lack of entropy, about processor performance, and about legacy and lightweight protocols. Now, updates actually are a big problem in the world of cybersecurity. Cybersecure systems need regular updates for quite a number of reasons. Algorithmic deprecation, bugs in cryptographic implementations, inertia of implementers' communities, software bugs, private key or PKI compromises are just some of the most important, and I will give you a few examples to promote understanding that these are really difficult problems. If we look at algorithm deprecation, we see a table of famous algorithms which after a while have been deprecated quite some time after their invention, and we see, well, many algorithms, even RSA, if we use short keys, invented, published the first time in 1977, deprecated in 2011, and even SHA-1 and SHA-2, which are quite well-known algorithms not invented so many years ago, these days should no longer be used. There could be crypto implementation bugs. Let's think, for example, of one very famous bug, Heartbleed. It made headline news in many areas, and it was an incorrect implementation of the heartbeat extension in OpenSSL. There was a missing array bounds check in a memcopy call, so actually, well, not a very deep-lying problem, but the problem was that it affected 66% of all web servers, and it allowed attackers to obtain usernames, passwords, session keys. So such bugs show up, they have to be repaired, new software has to be distributed, but the distribution of new software could take quite some time. The implementers community sometimes is astonishingly inert. Let's have a look at the PKCS #1 RSA signature forgery attack, which actually stayed active for 13 years. It was found by Daniel Bleichenbacher in 2006 and in 2014. Finally, in 2014, it was fixed in the Mozilla codebase, and it took until 2019 until it was fixed in OpenSWAN and StrongSWAN VPN systems. So it might really take a lot of time until these bugs are fixed. And there could be software bugs. Every software bug may eventually leverage into a security issue. And there could be private key or PKI compromises. The example I like most here is the one by Adobe, who simply published their private PGP key. You will be able to look at a screenshot of their blog and have a look at the literature reference pointing that out. It's just wonderful, a large company just by mistake publishing their private key. There is a famous security breach connected with the name of the former PKI instance, dnotar. They are no longer in business, and there is a fallback password of Zigbee, which is publicly known, and no doubt we will be hearing about that a little bit more throughout our summer school. So we understand update is a problem, but update is a particular problem in IoT scenarios. End users might not be aware of the necessities and procedures to update their light switch. Manufacturers will have strict end-of-life policies. They are no longer interested in fixing their equipment. It could be manufacturer negligence, and it could be device longevity. Phones have their life of 2, maybe 3 years. Then usually the next phone comes up. You want to buy that phone and the manufacturer doesn't bother to do updates for much longer. But if you think of facilities, of buildings, of nuclear power stations, they are in existence for 30 plus years. They certainly will need updates, and they need security updates. So it is not very much astonishing that the US government started to regulate requirements for devices which are used by them, by the US government. And they are going into fairly deep details. Devices must be patchable. It should be via a standard protocol. There should be no hard-coded and no static passwords. They should be free from vulnerabilities, defined as vulnerabilities which are known in the NIST, National Institute of Standards and Technology, National Vulnerability Database. There should be a removal of legal risks for good faith, security research, or for ethical hacking. So in case you do hacking with good faith, you shouldn't be punished. There shouldn't be a legal risk, but it should be a certain legal protection here. There should be a possibility for alternative network-level security requirements for limited devices. So there should be firewalls or intrusion protection systems. There should be guidelines for vulnerability disclosure if a vulnerability is found by a manufacturer. The manufacturer should be obliged to give notification about the vulnerability or about end of maintenance periods, and there should be an inventory of all IoT connected devices which are in use by the US government. So we understand they are starting to take these things quite seriously. And of course, we should also be looking into update mechanisms as such. Updates often take place in OTA, over-the-air scenarios. Updates via a network, via air, wirelessly, is like the fantasy behind that acronym. And we understand that there are a number of different architectures which might be used for that. It could be an edge-to-cloud update where every IoT device connects to the internet and receives an update directly from the remote server, as we find these things in Amazon Echo Dot, in Google Home, in Nest, thermostats, and similar devices. We could face situations of a gateway-to-cloud update where, well, every IoT device might be gateway connected, but has no own internet connection, and the update is sent to an internet-connected gateway, and the gateway now is responsible for managing a fleet of IoT devices, such as you might find in banking and financial services, in ATMs, in payment devices, and similar scenarios. And finally, there might be edge-to-gateway-to-cloud OTA updates, where IoT devices have only limited or sporadic gateway access. Updates are sent to an internet-connected gateway, and once in a while the IoT device might connect to the gateway. And here we have situations where we might have field-based sensors in agriculture, in looking for weather conditions or cultivation machine performance, and they are actually not always seeing their gateway, and once in a while when they see the gateway, we find these types of things. Remember, we said when we find solutions, the solutions also produce new questions, new problems, new attack vectors. So of course we could also think of updates as attacks. We have to counteract that. There must be verification. We must check the particular update for authenticity. We shouldn't here rely on shared secrets as they are required in symmetric methods and they might be distributed to unauthorized people. We should use asymmetric signatures on updates or on cryptographic hashes of these updates. We need recovery mechanisms. We need to allow automatic recovery from failed updates. There should be some possibility of rollback to previous updates. There should be factory resets. Okay, factory resets means we should allow manual factory reset on failed updates. But again, we must protect those against default password abuse after a factory reset. One idea could be a device-specific after reset password, which is not written onto the device for an attacker who is physically present to read. And the second idea would be an approach to needing a form of adoption process of the device into a gateway environment or into some software before we eventually start using this device. A second problem is lack of entropy. Why should there be no entropy? Well, IoT devices might not have a good source of entropy. The system complexity might be too small. There might be no human interaction available, which often is taken as entropy source. And after a firmware reset, similarly as in the password case earlier, all devices are nearly identical. They might be using a local MAC address for seeding pseudo-random number generators, but that's not really sufficient as true randomness. So there is actually also the possibility that we have no true hardware random number generator on the chip. If we look into the Intel line of processors, only the high-end processors, do have these hardware random number generators on their die. So we have bad entropy. And that actually amounts to these attacks we talked about earlier in the RSA case, where researchers downloaded from switches all over the internet certificates which had been generated on the switch and proved that these devices often have not sufficient entropy, and the factoring, we talked about that approach, worked out. There are a number of ideas here. One example, for example, here is the entropy as a service architecture, which is a NIST-proposed reference architecture. So we provide entropy as a service in the network, randomness through a network-based service. Actually, a very interesting thing. It allows the construction of new keys, of course, without that EAAS infrastructure, knowing which keys will be constructed here. It comes with a proof of freshness, but unfortunately, it doesn't have yet so wide of an adoption. Another aspect we should look into is processor performance. So I gave you here a link and a literature reference for a very nice overview on IoT processors as such. But if we look into the basic requirements of IoT processors, we understand it should be low price. In every light bulb, eventually we will see an IoT processor. So it can't be a very complicated type of equipment. There should be support for connectivity for all kinds of things, be it Bluetooth Low Energy, Z-Wave, Wi-Fi, what have you. Support for application protocols, MQTT, maybe banal things like HTTP, SMTP, or whatever. These things should be supported by an IoT processor. And the question is, are we there yet? Do we already know the generic IoT hardware architecture to a similar degree of precision as we understand it for servers? Well, the Xeon servers on the Intel line, they have hardware random number generators, for example. They have high performance. We know the generic server hardware architecture, but are we there yet with IoT? Let's have a look at two sides from the literature. RSA 2048 key lengths on an 80 Mega 128 processor takes 83 seconds. 83 seconds for a encryption process. Okay, admitted, that's in software, and the paper I took that reference from is from 2004. But in a 2015 paper, I found the following statement. Usually, IoT devices have limited computing power and memory capacity, and many cryptographic algorithms require more resources than tiny IoT devices possess. That is from 2015. Match this with a longevity of 30 plus years of these devices after their deployment. So, of course, the question is, can hardware acceleration, can hardware IP cores be a solution here? They can do fast crypto. They are available for cryptographic primitives, but not for all protocols. They are available for established concepts, but of course not for leading-edge research. It usually does not implement advanced crypto, a hardware IP crypto core. It cannot be updated, or rather, it cannot be easily updated and cheap at the same time. And we need high volume for the economic feasibility of building particular intellectual property cores for that purpose. And finally, if we look at legacy and lightweight protocols, we see there is still a wide range of different states of affairs in IoT systems, and security is living on many different layers of the stacks. Protocols have not always been designed with security in the mind of the inventor. So we see that there is a wide range of difficulties and challenges for IoT and SCADA if we look at it from the cryptographic perspective. In the written material you will now find an appendix with a number of references, a little bit of more information you might see, and we see it scrolling by. You might be interested in a few of these things and a few other references into the document. And now, finally, after a long journey into cryptographic basics, we are gonna discuss in an interactive event the details of how to connect our basic tools with the protection goals you have heard about in the first module of this kind. Thank you very much.